Okay, please go ahead.
All right, excellent. Yeah, we'll talk about biomass, forest carbon storage today. And this is a big deal for anthropogenic CO2 emissions on two aspects. One of them is that, as you well know, of course, deforestation, especially tropical deforestation, is a big deal. It accounts to 11% of the anthropogenic CO2 emissions as a mean over the past decade. But also, part of this carbon does not stay in the atmosphere and does not contribute to climate warming, but is captured by ecosystems. Especially 30% is taken by the land sources. So over time, when you look at these two contributions, land use emissions, that is to say deforestation mostly, is a positive effect to the increase of the carbon dioxide in the atmosphere. But this is offset in part by the sequestration in different ecosystems, and it's still a debate as to where this carbon is going. But we do think that forests are playing a large role in this effect. Okay, as for the sound, is it okay now? Can you hear me fine? Yeah? Okay, I can see you, but I'm assuming. If you need me to stop at any time, don't hesitate. Huh? Okay, the locking up carbon in forests is been deemed to be a manageable and important strategy for mitigating carbon emissions. In terms of quantitative aspect, this what's called this natural carbon solutions or climate solutions are really popular these days, are really important, and forests are the most natural way of dealing with this problem. Basically, planting a forest is a good deal, a good solution for the climate, and we all know this, and we've all heard about this many initiatives to plant trees, millions of trees, billions of trees, several billions of trees in different countries and different schemes. This makes sense, of course, but the point I'd like to make now is that this all ties into an economy, carbon markets, which are difficult to verify. And this is what I want to talk about today. So this carbon market have a fairly long history. This started for forests with the Reducing Emissions for Deforestation and Forest Degradation initiative, the RED and then RED Plus initiative, which was proposed over 15 years ago in Bali at COP13, and then implemented through the UNFCCC. But the Paris Agreement in 2015 established new rules for carbon market, especially country-based markets, and was open to forests as contributing to this carbon markets. And this is a very important shift, because then every country could claim forests to become a store of carbon and to be to profit from this store if at national scale, but also the companies could contribute to these markets, and this was envisioned already in the Paris Agreement. Now, you probably all know that this comes with a number of issues of double counting, carbon storage, the issues of geographical leakage, additionality, which is the fact that when your plan, you set aside forests for carbon storage, it should be something that is beneficial to the climate, is storing extra carbon that it would be if you would do nothing. There's been also a lot of local resistance to initiatives and issues about the stability of the carbon market. So this is not as easy as it may sound to establish a real a functioning carbon market. And I think many of you are experts in this area, so I'm looking forward to your questions. Then it came last year with this Glasgow's Leaders Declaration of Forest and Land Use, stating, and I quote, "A sustainable land use transition is essential to meeting the Paris Agreement goal, including reducing vulnerability to the impacts of climate change and holding the increase in the global average temperature to well below 2 degrees and pursuing efforts to limit it to 1.5. And the initiative was not only about fostering the role of forests into mitigating this carbon storage opportunities, but also land use change was very important in this declaration. Now, a real problem in all these political arenas is that we tend to forget that measuring carbon in forest is a difficult business. Now, on the left of this slide, you see a map of trees seen from above with tree locations and tree sizes materialized. This is actually, I draw this with random number generators. This is not real data, but you see that biomass is not located continuously. It's not a continuous variable over space. It's actually point-wise variable, and it's biomass is actually where the trees are. So you cannot really define the biomass density over space if you don't define the biomass over a certain area. And in addition, it's very difficult to measure biomass as a quantity. It takes cutting down the tree and weighting it, and then taking the next tree and weighting it, and so forth. So all of what we know about biomass storage is based on indirect statistical models that relate biometric dimensions such as trunk diameter, trunk height, tree height, and wood density to this quantity that we are interested in today, biomass. And I'll be talking mostly about above ground biomass, ignoring the below ground components because it's even more difficult to access it, but we of course should acknowledge this is a very important component. Another problem that we are faced with is that we have a very uneven distribution of knowledge about the biomass stocks in forest geographically and especially latitudinally. We have a lot of information about national forest inventories in the temperate zone, especially in the northern hemisphere, but we have a lack of this information massively in the tropics. And this is a huge problem because the majority of the carbon storage today are in the tropics. So if we are to establish long-term carbon storage programs in the tropics, we need to be able to verify that they are actually carbon stocks and they actually do sequester carbon, and we need tools for that. So the classic approach is to establish ground inventories of plots, such as what I was showing in the previous slide, that it's very expensive, time-consuming, and difficult to achieve in the tropics. Other aspect is to try to think about other technologies. One of them is LiDAR, which is an amazing technology, and this is based on sending photons, beams from aircraft or whatever vehicle from the air, looking downwards, and the retro-diffused quantity of this waveform is recorded in real time, and is also geolocated and allows to access directly quantities such as the canopy height and the topography below the canopy of a forest. But it is also applied for many other very interesting applications, as you may know, such as archaeology, discovering lost cities that are now covered in vegetation. So it's a really interesting application. So it really looks like this is a cloud of point that where you actually do see, when you're looking at a forest using LiDAR, you actually do see the trees. So question of whether we can translate this information into biomass estimates has been asked, and the answer is yes, to an extent, because canopy height is proportional to biomass. And so a lot of projects have been developed to estimate a biomass using airborne LiDAR sensing. which is really interesting because you can cover thousands of hectares of land as opposed to a few hectares when you're going by foot and measuring tree one at a time with the classic forest inventory applications. Now, an even more impressive application has been to put the first LiDAR on a satellite. So this is really a nice example of serendipity where the satellite was developed to measure the height, the changes in the depth of ice in the polar caps. And of course, to measure both caps, the satellite had to measure all the Earth. And the engineers working with this project discovered that they had a lot of information to extract as a really valuable information in forests. And this image shows the path of the satellite over the Amazon, showing that there was a lot of information from the satellite LiDAR. So the question was asked whether we could use this information to establish the first canopy height model of the forest at a global scale. It's quite developed by colleagues such as Mark Simard and Sasan Sachi, in both working at GPL and with NASA for a decade ago now. And a new application has been a major advance over the past few years, and it's called the JEDI satellite. It's the new generation compared to ISAT. It's not a satellite. It's an instrument on board the International Space Station. The project was started in 2019 and is about to end, although there is a pressure from the scientific community to continue this project because it's such a massive success. And the idea is the same, but the density of points of these LiDAR points is much more important. So the left panel here shows from top to bottom the altitude, and shows that the reflected signal is very important at the top of the canopy and then at the ground level. So you can, from this information, on every spot measured by this the JEDI instrument, you can measure the canopy height, an estimate of the canopy height of a forest. And the rightmost part of my slide here shows that you have sampling strategies. It's not really a full coverage of the world. It's really a sampling strategy where points are being shot at a resolution at a spatial resolution of about 600 meters on the side and a few hundred meters actually, and covering low intensity laser beams and high intensity power beams. And combining this with models, you can come up with a canopy height model with very high density of points, as shown here. This is the extraction of data that are freely available. And I provide the link here at the bottom of my slide. I'm working in the tropics. I've been working there for quite a number of years, especially in this territory, which is technically part of Europe. It's French Guiana, so it's a French territory in the Amazon forest. It's not in the Amazon watershed, but it's in the Amazon. And because I was interested in that part of the world, I zoomed in for you, and you see a number of features. First of all, the canopy is very high, it's very tall in this part of the world. It's over 40 meters on average over the entire area. Second, you see that JEDI is doing a really great job at densely sensing the canopy height, but has a number of missing areas. And this is due to cloud cover, it's due to problems with precipitation and problem with coverage. So the coverage is not uniform across this region. And this is, of course, it's the best we can do today, but it's not ideal. But this is really the state of the art as of today, November 2022. And so it's really great to see how much progress has been made. Of course, based on spatial modeling, you can construct a full wall-to-wall map of the entire world with canopy height. And you can also extract from this canopy height, or infer rather from this canopy height model, a value of above ground biomass. And this is what I'm showing conceptually in this slide. The idea is, again, to go statistical, to say a taller canopy will hold more biomass. And because we have ground data, we can establish a model comparing the above ground biomass to above ground canopy height. No, you can do this, but you intuitively, it's pretty clear that you cannot go to very fine mesh density of points, because then you enter the problems, which is what I'm trying to show in this slide, that a very large trunk, a very large tree will create a lot of stochasticity within the statistical model comparing canopy height and above ground biomass. So the strategy here is to define above ground biomass density at a 1 hectare resolution, which is 100 by 100 meters, and to construct a statistical model that compares the canopy height to above ground biomass, and to therefore to be able to construct an above ground biomass map. There is no reason why this model, which is purely statistical, should be the same in the Amazon and in African rainforest, or in Europe. So the big problem is how much we need to calibrate or recalibrate those models in different parts of the world. They are not mechanistic, so in that sense, it's not really satisfactory. But it's been done by the science team of the JEDI science team, and this project is being published now. Some above ground biomass maps are being published now. In a sense, what the major problem of JEDI is that it's not long term. So going back to my introduction, that we want to have a tool that will be able to measure carbon stocks in the forest for a long time in the future. JEDI is not the best solution for the moment. It's a great idea, it's a great step forward, but not yet there. So we proposed as a team in 2014 a new satellite with a completely different design called BIOMASS, and it will be launched sometime in the future, fourth quarter of 2023, more likely first quarter of 2024. Those are massive projects. This is how it looks like. Just take a tour of the owner here. It's yours because it's an international project, as it is mine. And this is a very big satellite. The reflector is 12 meters across. This is the larger reflector for a radar sensor that will be sent to space. This is a very massive project. In terms of the technology in there. It will be a heliosynchronous orbit over 60 kilometers, 600 kilometers above ground, and will be sensing the entire world for during a period of slightly over 1 year. Okay, I'm stopping here. You've seen enough of that part. Moving on. So the primary mission objectives of this satellite is to reduce the major uncertainties in carbon fluxes linked to land use change, forest degradation, and regrowth. It's also to provide support for international agreement like UNFCCC's, especially the REDD+, but also the Paris Agreement. Infer landscape carbon dynamics and supporting predictions of models, of land surface models. It will also be helpful in initializing and testing the land component of Earth system models, I was saying that, and provide key information on forest resources, ecosystem services, biodiversity, and conservation, on the premise that more carbon-rich forests are also those that are more biodiverse. There are also a number of interesting secondary objectives, but the ICE-SAT story that I was explaining before tells us that we should not exclude or ignore those secondary objectives. There is a very interesting application for subsurface geology in desert, especially exploring the deltas, hidden deltas in the Sahara, where paleo cities were used to exist. there a few thousand years ago, construct very fine resolution digital terrain models at the global scale, which is still not available, especially in densely forested forest areas. And to look into the glacier and ice sheet change velocities. So this is something that is more interesting in polar caps, and that I will obviously not be talking too much about today. Biomass will provide three key informations, types of data. First, forest biomass, obviously. It will provide above ground biomass density in tons per hectare at a 4-hectare resolution, 200-meter resolution on linear size, with one map every 6 months, an initial map for 14 months. It will take 14 months to obtain the first map, and then one map every 6 months for 4 years. It will provide a global coverage of forested areas with an accuracy, target accuracy, should say, of 20% above 50 tons per hectare, and at least an accuracy of 10 tons per hectare below that. I should say that biomass is really designed, and I'll explain that later, for the high carbon density forests. Other technologies are more appropriate for the low carbon density ecosystems. It will biomass will also provide a forest height model, which is really interesting because it will be comparable to JEDI, also at 200-meter resolution, and with a global accuracy and with a global coverage and an accuracy of 20 to 30%. And it will also provide an information about disturbances at 50-meter resolution. Now, of course, for disturbances, many other technologies, including technologies using ongoing the Sentinel-1 satellite, are already functioning. So it will be more of a cross-check of the technology rather than a primary input, but it will still be quite useful. And the international context for this, I've already said that it was in the terms of the international context of the UNFCCC will be really important, but also it will hopefully also provide crucial information for to verify carbon standards, and there are several of them for verification, and also for the modeling community. Okay, now this is the context. Now I'd like to share with you, if you like, a few technological aspects. I'm a bit behind schedule. If you don't mind, I'll go ahead and I'll see how it goes. Now, I think in your community, you're interested in some of the technological aspects, so I'm sharing this with you, but I hope I'm not going too far away. The idea of biomass as a satellite is to look to quantify, to estimate biomass from space with a very different technology from LiDAR. It's a radar. And the idea of a radar is that the longer the wavelengths, so I have this animation, I'll show the whole of it in one go. The longer the wavelength of the radar electromagnetic wave, the broader the objects you actually see, in a sense, in a broad sense, where you don't actually see things, but you sense them. So in X bands, which is 3 centimeters, you see the leaves of a tree. In L band, which is 27 centimeters, you see the branches and fine details. And in P band, which is what biomass proposes to be launched as a technology for the first time in space, you see the broader features like large branches and trunks. And this is the core concept behind biomass, is that P band is seeing the forest the way we ought to be seeing it, to quantify biomass, because it sees the larger components and it strips away the things we don't really want to see, which is the leaves, because the biomass content of leaves is pretty much negligible in a forest. Okay. Another way to put it, as a colleague of mine is showing, this is really the top, the ultimate level of evolution for remote sensing technology, coming from the visible all the way to P-band synthetic aperture radar. LiDAR is also very cool, as I tried to convince you before. Okay, so the first thing synthetic aperture LiDAR radar is doing is to send a wave in different polarizations. It sends, transmits horizontal waves and then takes back from the backscattered intensity horizontal waves, but it can also sense the by sending the horizontal waves, send what is being backscattered vertically, which is the HV polarization, and VV is transmission vertically and received vertically. So what we measure here is the intensity of the backscattered signal, and I will call this delta. Now, a second point is that intuitively you have, well, I mean, it's not so intuitive, but sending a wave to any object, any rough object from above, from space, you can have three basic components. The ground contribution, which is very simple, it's just a reflection. You may have in a complex system like a forest, a double bounce effect, which is what I am trying to illustrate here at the rightmost part of this bounce, of this panel here. And the last part, the third part, is what we actually are interested in, is the volume contribution. The more complex the forest, the more backscatter there is. So if we are able to take apart those three components, we may do something with this data in terms of estimating the intensity of the backscattered signal, relating it to forest above ground biomass. Now, there is the math there behind this is not super complicated, but it's not super simple either. There are equations to relate the intensity of the backscattered signal for the volumetric component, for the double bounce and ground components, and combining them together, you can estimate the parameters of this model with regard to ground data for calibration purposes, and then you may extrapolate this information. So I just wanted to show you the equation a little bit because they're not too complex, and you see the diffusion effect, the angle effect, because the signal is not coming from right above, but from an angle. And you see that it's kind of makes sense, right? Even if I don't want to delve into all the mathematical details here, it's not the purpose of the talk today. Now, this one model has 18 parameters, and they can be inferred by the model fitting, And once the model parameters are fitted in a region of interest, they can be extrapolated elsewhere. Again, we have the same problem as for JEDI. We don't exactly know how far across a calibration site we can extrapolate, but this is something I'll go back to this at the very end. Biomass retrieval information is retrieved in a volume effect, and removing the effect of ground and double bounce is kind of difficult in convergence of the algorithm. Also depends on the quality of the validation data. Now, this is fortunately not the only type of data approach of analytical method we have with this type of sensor. And I'll show you two more in a more intuitive way. One of them is not only take one orbit cycle, but take two with a slightly different angle. And this is called interferometry. So with this information, you not only have the intensity of the backscatter signal, HH, HV, and VV, but also the phase difference. And that provides very valuable information to provide a sense of the canopy height. No, I won't prove it to you because again, it will be really a bit too much of a time, but I hope I give you the sense of this second technology of polarimetry plus interferometry, which is called with a nice nickname of POLINSAR in the field. A third approach is to do the same thing, but with many more layers. And this is a site akin to tomography. If you see the same object with many different angles, then you start to reconstruct in 3D the system. Especially you start to look at different canopy layers. This is really the idea of radar tomography. And this is actually working. This is fantastic, really major events of SAR technology to be able to do tomography with this type of data. So again, this is just the intuitive idea that I'm showing to you. But we now have three approaches: polarimetry, SAR, and tomography. And they all serve the purpose. Now, we've been testing all these approaches at very limited sites with airborne P-band radar to see how well they were featuring. TomoSAR, tomography with radar, has been tested and seems to be working really well, actually, especially in the high carbon forest. Therefore, we decided to allocate the first 14 months of the mission just to construct a very high quality biomass map of the world. And in the second step of the biomass mission, now I'm showing the quality of the data of this TomoSAR approach based on ground data. This is the map of a site in French Guiana where we did the first tests in 2009. And the fit of the data with this approach is really good. The reason why it's very good is that it's very the more noise, the most serious noise we have with the SAR approach is from the ground. But with tomography, you can take away the ground and look at where most of the carbon is in the higher level of the canopy. It's really explaining this intuitively. The second phase of the BioSAR mission will be to look at the SAR approach. So it's cheaper in the sense that you don't need as many orbits, so it's a quicker approach, and you can cover a space in only a bit more than a year, half a year, 7 months. You can cover the entire world with this. So the idea behind this is that we can cover every 7 months with starting with the baseline of the TomoSAR map. Every 7 months, you will have a new map with changes. And this is what we are mostly interested in is carbon changes in forests. Now, this is the type of data we get from SAR from the same site in Parakou, French Guiana. Okay, now I'm going to show you exactly the same thing in a short presentation that was given to me yesterday by ESA, by the European Space Agency. So this is basically biomass looking at the forest with its, so to say, eyes, striping away the leaves and looking at the branches and the trunks. Now, the first approach is to take just one go, and by doing so, you have the backscattered intensity by polarimetry, and you have the different color schemes are the amount of biomass you get from a very simple model like the diffusion model I was showing. The second approach is to take 2 goes and using a SAR, and then you have a sense of the height of the forest. Height of the forest is much better, of course, than just polarimetry, but it's you can do even better. So the third approach is to stack many layers. I hope you see the different layers that are being stacked here. And here you may not see the slight difference, but what we are able to do with this data is to look into the forest. And that is, of course, much more precise in terms of biomass retrieval. Okay, so moving on, the last point I wanted to cover real quick is that there is no magic here. We still need to train the algorithms and validate the data at the end of the day. So we need, for biomass timely forests data, we need a lot of ground data, which should be measured at the same time that the biomass satellite is flying. We need a wide geographical spread with many different forest types, because otherwise we'll be never sure that the model we've calibrated in one forest is valid in another forest. We need also high quality data. By this I mean forest inventories that can actually be converted into above ground biomass estimate, and it's difficult You don't only need diameter measurements, you also need wood density measurements and tree height information. So all of this information has to be measured on the ground, and it takes time and it takes money then, therefore. And we call this initiative, so it's, sorry about the typo, it's called GeoTrees, and I'll show that later on. We also have worked on a product validation protocol with that's validated by a number of systems, but it's under the auspices of the Committee of Earth Observation Satellites. Now, the GeoTrees initiative, and not EGeoTrees, is an initiative that we've started a few months ago. I'm heavily involved in this, so I'd like to advertise it, if I may. It's this initiative is set out to establish a global network of high-quality biomass reference day measurement sites, and we want really to have classical forest sense data in different forests, but especially in the tropics where the data are missing the most. We want to combine at the same site forest inventories and airborne LiDAR data, and if possible, to combine them with terrestrial or drone-based LiDAR, because they would provide also three-dimensional high-resolution rendition of the trees that could be helpful also to provide better accuracy to our ground data. The type of sites we are covering here are, and we've shown this in this paper in Press and Global Change Biology, seem to be quite representative of the entire diversity of tropical of forests globally, temperate, boreal, and tropical, based on just, so to say, 100 sites. 100 sites with a lot of good ground data is still very difficult to achieve. It will take a major effort, and we will have to build on existing networks, such as the Forest Plot Network, which is run from the University of Leeds in the UK, ForestGeo, which is run from the Smithsonian Institution, TMFO, which is Tropical Managed Forest Observatory. All of them are tropical forests, or some of them temperate, including temperate and boreal forest, permanent sites already supported with stability, where we need to ensure that we have good data coming from them in the forthcoming decade. The estimated cost of this initiative is between 50 to 100 million, which is not cheap, I would say, but much cheaper than any of the other satellites. BIOMASS is in the ballpark of 500 to 600 million euros alone, and many other satellites in the same community of satellites are much more expensive. So we need good ground data. It's not cheap, but it's much cheaper than launching the satellite, and they won't do without us. Eventually, the value is that this type of data is trusted and eventually used by the carbon markets, and especially verification systems, and by anyone who wants to buy carbon credits should be able to verify themselves using this type of data, whether the forest that was promised to them is actually being planted or grown. So as way of a conclusion, forest sequestration is an effective method to offset carbon emissions. However, how and where these carbon sequestration projects are conducted is often vague in the current carbon market business, and national legislations are very difficult to enforce, or sometimes rife with loopholes and other problems. Second, a verification mechanism for trading forest carbon credits must rely on a global, near real-time forest monitoring system. And remote sensing, I hope I convinced you a little bit that remote sensing can help if and only if a representative set of ground data is made available for the validation of these map products. And so if we don't achieve that third step, governments and institutions will doubt their utility, and they will not simply not be used for this application. They will still be very important and useful for science applications, and that's not nothing, but this will fall short of our goal, and it would be a bit of a shame. Okay, I'll conclude saying that this initiative of the GeoTrees will foster collaboration and share the cost between the people on the ground doing hard work and institutions usually more in the global north than in the global south. With this, I'll thank you for your attention. Take any question if there is some time left. Thank you very much.
Thank you very much. Jerome, can you hear me here, please?
I can, yes. Yes.
Very good. Okay. So we have something working. Okay, we're open for questions. Anybody want to? Orlando? Yeah.
Was I correct in understanding that the lifetime of the satellite was a year?
I'm sorry, I couldn't hear the last part of your question.
The question was, is the lifetime of the satellite 1 year?
No, the lifetime of the satellite is 5 years. Many of the Earth Explorer initiative have lasted more than 5 years, actually. So we could be optimistic and think that it may last for up to 10 years. So it's a long time scale.
Thank you. Any other? Yeah.
I was just wondering, can the P-band radar distinguish between the different layers of the rainforest? So between the canopy and the understory, is it precise enough? And secondly, is there any hope of JEDI being renewed, do you think, so that it overlaps with the data gathering from biomass?
So the first question was about the use of looking into below canopy biomass.
Yeah,
I didn't understand that.
Can you determine between the different layers of the rainforest, or between the emergent or the understory, or is it do you view the below canopy data as one big layer?
Yeah, it's really good question. So with tomography, you can really slice horizontally the forest and look at the different contributions. For the moment, we're interested in the bulk contribution of all this information in terms of biomass. Can we use all of it and provide the best estimate of biomass? The second objective would be to look into the more detailed information at the different layers and ask whether they provide some extra information like we do with LiDAR. So for the moment, it's still work in progress. We have very few data in P-band airborne radar. So I can't really answer the question as to whether we can do more than what we aim to do here. As for the second question of the JEDI, the plan from NASA, or at least for the JEDI science team, is trying to push very hard and that the JEDI instrument is not sent back to Earth, but is kept in the International Space Station. The slot of JEDI has to be used for another instrument. I think, unfortunately, well, military application, so non-negotiable. But after a couple of years, it should be done with this application, and JEDI would be put back. So if NASA gives a go to this option, that would be really interesting, because we would have another term of JEDI data coming in. There was another option from the Japanese JAXA satellite agency to send another instrument called MOLI, but we've not heard much about MOLI, and I'm not sure, I cannot report on any future for this initiative, but it was quite similar to JEDI. I also forget to say that there is another satellite, which is the sequel of ISAT, called ISAT-2, which is a proper satellite and provides interesting data also. It's not really designed for this specific forest application, but the data are really quite interesting as well.
Thank you, that's fascinating.
David?
I wasn't going to, but I will then. Do you know what's happening with the military issues of the P-band being similar to the missile detection systems and all that, and having to turn it off? What's happening there? Is it going to be global, or is it going to be turned off over parts of the world?
Thanks, David. Hi, by the way. Yes, I was trying to avoid this itchy detail. So we were hopeful a few years ago that the Department of Defense of the US would allow us to fly satellite globally. It so happened that P-band was actually for military use until 1992, because it's used for radar for space object tracking devices, or also SOTR or whatever. And so all of the North America is covered with this from the Cold War era. It so happens also that there is one station in the UK. You may not know that, but it's covering the entire West Europe and NATO basically. And so all of this area is a no-fly zone for the instrument. So as soon as the instrument is above this area, it has to shut down the instrument. So a few years ago, we were kind of somewhat optimistic that we could turn around the DoD and enforce and that they would allow us to use the satellite. Since February 2022, I'm not so optimistic. So for the moment, North America and Europe, Western Europe, is off the grid. We don't have a lot of tropical forests in these areas and high carbon stock forests, as you may know, and we have a lot of capacity other than biomass. So it's not dramatic. It could be better though. So it's life.
Anyone? Yes, okay, Chave.
I'd be interested to hear your thoughts about the resolution of the satellite. It's obviously in sort of intact wide biomass forest, 200 meters should be fine, but if we're detecting change, degradation, regeneration, a lot of these events can happen at a smaller resolution. So be interested to hear your thoughts on how we can kind of tackle those problems.
Yeah, thanks very much. As I was trying to say, this quantity, this biomass dense is actually density. And if you reduce the spatial resolution, it's actually not a continuous quantity. It's like a bunch of point-wise Dirac spikes, which are actual trees. And so it doesn't make really much sense to measure carbon density over a very small resolution. As a density, it's also, although it's very valuable because a lot of the biomass is outside forest, is in individual trees, there are lone trees, tree outside forests, so to say. Biomass is not really addressing this problem. However, spatial resolution optical imagery has proven to be really good to detect these isolated trees or clumps of trees that are outside forests. And so we're looking really at complementary technologies here. Biomass will be really good for high canopy, high carbon density forests, especially in the tropics. Then high resolution optical imagery will be complementary to provide insights into the densities of trees outside forest. There's been a really nice string of papers led by Martin Brandt in Copenhagen, where is developing artificial intelligence to detect this lone tree outside forest in many ecosystems, arid ecosystem especially. I hope I addressed your question, but as for the baseline 200 meters, it's also bound by limitations of the technology. The minimal resolution of the satellite is 55 meters by design.
Any other? Yes.
Just a very short question. I wonder what would be the data formats of biomass in the future? How accessible or compatible it is with the current deep learning framework such as PyTorch? Or how much time I need to spend on data pre-processing before starting the model training using deep learning models?
I'm sorry, you were cut. I couldn't hear the last part of your question.
Let me try and repeat the question. The question was, how compatible will the data format of the biomass satellite be with existing training frameworks for AI such as PyTorch?
Okay. All right. So I'm out of my breath here. All I can say is that for the first time, NASA and ESA have joined forces to make sure that all the data they're producing, and there are massive amounts of data. There's one satellite I forgot to mention is NISAR, which will be launched as a joint venture from NASA and ISRO, the Indian Space Agency. also in 2024. And all of this information is bound to be part of the same platform, which called the multi-algorithm analytic platform, the MAP, MAAP. And this platform will contain not only all the data readily accessible, but also a lot of software capacity, analytical capacity in the same type of format. And this is really a joint venture from NASA and ESA. So in terms of access to the data and formatting, there has been recently a lot of effort to try not to duplicate things and try to provide a platform for, especially for scientists, but also for users to do their on the go. No, I'm not too sure. I will not be able to comment on as to whether PyTorch will be available already in this platform, and that it will be just a piece of cake for you to do the work. I honestly doubt it, but I don't know.
Thank you. One last question. Oh, this one on that. Thank you. Yes. Okay. So the question is, Jerome, can you see the question online on the chat? I'll read it out to you.
Yes, I'm curious about the library assessment to select location from ground truthing. I'd be really interested to see the paper, understand how the selection was made. You think cover the range of degradation, restoration condition, as well as forest types. Thank you very much for the question. Really good question. No, the first criterion for selecting the sites is the site already established? We don't want to start to engage into establishing sites that we know nothing about in random places. We just can't afford to do this. It would be orders of magnitude more expensive and with no reliability in terms of geopolitical situation to be successful. So we're starting from the sites we know that have been stable over the past couple of decades, that are already some data available, and we want to gap fill this data and also remeasure sites. So that's the first point. Then we're going for 100 sites because 100 is a round number, but we will see how far we can go. For the moment, we are collecting data on 5 sites, which is really short from the 100 site target, but we don't have all the money. We're trying to raise the funds. Now, in terms of representativeness, if this is an English word, of this network of sites compared to the diversity of forests, we are trying to cover all forest types, the broad forest ecological zones. So this is one part of the answer. And the Labrador paper was interested in trying to assess whether environmentally we are covering all types of bioclimatic zones and all types of ecoclimatic conditions. And the answer is, yeah, pretty much. Not perfect. We still are missing some types, but we are doing pretty well. Also, we have small forest plots, but we also have a coverage of 1,000 hectares at least of airborne LiDAR coverage of the forest around. And most tropical forests these days are not pristine canopy cover. They are including in forests in different types of degradation, of restoration. So we hope that we can cover this issue that you're raising in the question by looking at the landscape level and only at a few tree plots. So maybe we can do better. I really hope that we can rely on other initiatives, but this is the strategy we've come up with, and we'll try to implement it. Thanks.
Thanks a lot, Jerome.
Thank you very much. Let's thank Jerome.
Thank you.
Thanks a lot, everyone. My apologies for the audio problems, but hopefully we sorted it out. Thank you, and we'll see you next week.
Jerome.
Thank you.
Bye.
Bye-bye.
Cheers.
Hi, Jerome.